The basic functionalities of a mixing loop is that it gives us the opportunity to mix up water. And that means that we can mix up whatever temperature that we need in a heating or a cooling system. And basically the mixing loop consists of 3 parts. We have a pump, we have a bypass, and we have a control valve. The water flows in this direction. It comes here and goes up through the pump and to the consumer, where it's cooled off. It returns in this pipe this way through the control valve and back to the district heating system. The valve is a modulating type. That means if we have increased performance need, the valve opens, and if the need is decreasing, we close the valve. And by doing that, we actually force some of the return water from the system into the bypass and into the flow pipe. And since this water is cooled water, we mix it up here. This is the mixing point. The water coming from here is hot water, and the water coming from the return is cooled water. And when that is mixed, we have a third temperature here on the flow side. That's the principle in the mixing loop. On the flow pipe, there is a temperature sensor installed. It monitors the temperature and sends back the signal to the building's BMS system, which opens and closes the control valve. And in that way, we can always control the flow temperature in the system. The flow temperature to the system is right now 28 degrees Celsius, and the return temperature is around 25 degrees Celsius. That means there's a delta T of only 3 degrees, and that is actually a very low performance on the system right now. In a maximum load situation, this system is actually designed for a delta T of maybe 30 or 35 degrees Celsius. On both sides, we find balancing valves. There's one here, and there's one here. And the balancing valves are used for balancing the water flow on both sides. Even though we have a pump that's adaptable, it's very common to find balancing valves both on primary and secondary side. And that is simply to commission the water flow so we don't have overflow in a system like that. Overflow on one zone, like this one for example, is a problem for a building, because that means that you have too high performance in the system, but it also has a consequence of other zones in the system. In this building, there's a number of zones with their own mixing loop. But if we have one mixing loop taking too big a share of the water, then the other mixing loops, they are getting too little water, which creates underheating in those areas that they are serving. That means that balancing of systems on zones is very, very important. The pump used in this zone here is a Magna pump. It's an older model. It's still good, but however now we have the Magna 3 pump, and actually we have the flow limit built into that. That means on the secondary side, in a system like this, in a mixing loop, we can actually save the balancing valve here. Here we have a pressure differential control valve. And this valve ensures that we have a stable pressure on the mixing loop's primary side. And that is important for the control valve it enables the control valve to achieve a more stable regulation. On the return side of the mixing loop, we find another temperature sensor, and this sensor monitors the return temperature from the system. And since this system is connected to a district heating plant, it's very important that we are having a sufficiently low return temperature from our systems. And that is important for the district heating plant, because the lower temperature that we have here, the higher efficiency they can achieve on the district heating plant. So, just to recap, mixing loops, whether it's sitting in a heating system like this or in a cooling system, it allows us to adapt both the flow temperature in the system and also the flow in the system, which enables us to achieve higher controllability in the system and also achieving a better comfort. This is an example of a mixing loop in a heating system. It's a pretty modest size we're talking about here, a small Magna pump. And on this side we have also alpha pumps. But mixing loops are also very common in cooling systems. So let's take a look at that. Mixing loops in chilled water systems, they are usually larger than the ones we find in heating systems. And that is, of course, because we have a much lower delta T in a system like this. In a heating system, we can have a delta T of 25, 30, 35 degrees Celsius. In a chilled water system, it's only maybe 5, 6, 7 degrees. And that means that we have larger pipe sizes, we have larger flows, we also have larger pumps, of course. What we can see here in the picture now is the primary side of the system, and let's take a look at the secondary side now. So let's take a look at what's above us. And basically here we find the secondary side of the mixing loop. Here we have the bypass, we have a pump, and in this case it's a Grundfos TPE pump with a on-built or integrated frequency inverter. We have a balancing valve again, and we have some thermometers, and finally we have a strainer. This mixing loop basically only supplies one consumer, and that is a cooling coil in the air handler unit. So let's take a brief look at that. What we see here is a part of the air handling unit. Here we see the cooling coil sitting here, and here is the water coming from the mixing loop. It enters the cooling coil down here, and it leaves the cooling coil here. And basically the purpose of this is, of course, to chill the incoming air. Depending on where we are in the world, the incoming air has more or less moisture. And by cooling the air, a part of this moisture, or maybe it all, will condensate. And that is done in the cooling coil. And in order to collect that, you have to have a condensate tray under the cooling coil, as well as a drain connected to it. So let's take a look at the cooling coil itself. Be careful now. Now there's a lot of wind